Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 32. We are in lecture 15, part C, and we are going to finish up confidence intervals for the means. So we're going to talk about the third case here. And the third and fourth case, we do not know sigma squared. And in this first case, we're going to have n less than 30, and for case 4, n is going to be greater than or equal to 30. So the modified standardized form is z of x bar. Now it's x bar minus mu over s over the square root of n because we don't know sigma. Okay? And so we still have the same requirement that the data must be from a normal distribution, and now z has a t distribution with n minus 1 degrees of freedom. The proof of that is given here. So we have this theorem that we proved last semester that z has a standard normal distribution, w has a chi-squared distribution with r degrees of freedom, they're independent, and z divided by the square root of w divided by its degrees of freedom has a t distribution with degrees of freedom r. X bar and s squared are the mean and variance, respectively, of a random sample of size n from a normal distribution. If they are, then we proved again that z was a standard normal distribution. Let w be n minus 1 times s squared over sigma squared. We showed that that has a chi-squared distribution with n minus 1 degrees of freedom. We also proved they were independent, and we could construct a t statistic by taking this z divided by w over r. Well, r here is n minus 1. And I've already done this, so you can follow through and substitute in. You'll see that things cancel out, and we end up with this form here. And because we have n minus 1 here, that's r, we have n minus 1 degrees of freedom for this t statistic. We've already talked about the properties of the t distribution last semester, but we'll talk about it briefly again. It's symmetric, mean zero. It's similar in shape to the standard normal distribution, but it has heavier or thicker tails. So that means that if this is the standard normal, then it can't be as high because they both have area of 1. And so the t would be here and z would be here. So the t distribution has thicker or higher, heavier tails. It's actually a family of distributions. The t distribution is a family of distributions. Each is a different distribution for every single different degree of freedom. As the degrees of freedom increases, the t distribution converges to the normal distribution, the standard normal distribution. The expected value of t is the mean, it's 0, and the variance is r divided by r minus 2. Now remember, if r is equal to 2, we're dividing by 0. And if r is 1, then that would make this negative, and the variance can't be negative, so the variance does not exist for r equals 1 or 2. It only exists for r equals 3 or higher. Okay? And if you look at it, it looks like a standard normal distribution, but it's, again, has thicker tails. If you compared it to the standard normal, you'd see it's different. Now, to read the t-table, we learned how to do this last semester, so I'm just going to briefly describe this. These numbers are phi of t. They're the CDF. And then this is a critical value. And the way it's defined is that if we have a subscript, here is 0.4, then that would be my subscript here. And the area above this value is that subscript. Okay, so that subscript is the area above the value. So unlike the z-table, this is exactly opposite. This is a t value. This is t sub 0.4, 1, with 1 degree of freedom. That's what that value is. So inside the table are the t values. In the z-table, inside it are the probabilities. Here the probabilities are outside it, above it, but we also have degrees of freedom, r. Okay? And let's do we'll do one of each of these, and I'll let you practice the others on your own. I've written the answers over here for you, so we can see how to do that. All right, so we want to find the probability that t is greater than 1.33, and it has a degrees of freedom of 18. 1.33, 18. So we come down to 18, and what I can do is draw this over until I get to 1.33. And this says less than, and the less than is here, so that would be 0.9. Oops, I went to the wrong thing. So this is 0.90. Oh, I'm sorry, this said greater than. This one's 0.0, okay. Here, this is 0.90. This is the less than. And so the greater than is going to be this number right here. Oops. So it's 0.1, the remainder. So this is less than here. So this goes with this line. And this is the probability that t is greater than t naught, or t sub alpha. And so that's the 0.1. So the first one is 0.10. And so that's how you find these. And we can do a different number and we get a different value. So now we're going to have a 10 degrees of freedom. And we're going to look at, says that from there we know that this is 0.05. Use symmetry to determine these others. So this is going to be the 1 minus that. Okay? So this is greater than. So these answers aren't right after all. So let's ignore those. And then, so if we have that greater than this is 0.05, always better to draw. And so this is 0.95, and then this is 0. And so remember that above here is 0.50, and we want between 0.812. We want this area between here. Then we need to subtract these two, and we get 0.45. Okay? And then for this one, we want between 0 and the negative value. This is symmetric. It's going to be the same as this one by symmetry. And then we say we want from the negative to the positive. Well, it's going to be 2 times the 0.45, which is 0.90. Okay. Because it's twice this, or this and this added together. Okay, so we did those. And this is looking for the critical value, t naught, okay? So it says that this is 15, so 15 degrees of freedom, and we have that the alpha, or the value above it, is 0.01 for 15 degrees of freedom. Let's clear this. And we'll come to 15 degrees of freedom here. And we know that the area above it is 0.01. So we are right here. And so that means that this is 2.06. This is 15. Okay? So we want to know the t value. The t value is 2.602. So t naught equals 2.602. Oh, we want less than. So this is going to be negative. Remember, we just looked up the positive. We said, okay, so the area above it is 0.01, okay? And that is 2.602. And this says less than, so that means by symmetry it'd be negative 2.602 would have the same area below it. All right. So we have to be careful here. That's a negative. The next one says if 0.05 is below it, we want to find t naught. So it's still less than. So if we find the one for 0.05, and we find T naught, then we need negative T naught is what we find. We need T naught, which is going to be negative, and this will be 0.05 as well. So we have 15 degrees of freedom. We look for, we look for 0.05, and here is 0.05, and so the positive value is going to be 1.753. So this is going to be 1.753, and so T naught will be negative 1.753. So T naught equals negative 1.753. We need the negative of it. And then we want the probability between negative T naught and positive T naught to be 0.95. And so if we have 0.95 here, then this has to be 0.025, this has to be 0.025, and so we'll find T naught by looking up 0.025 above, get the positive value. Oops, don't want to do that. So we need 0.025 above. That's going to be here, 2.131. So this is 2.131. This is negative 2.131. So T naught equals 2.131. And then, which I had here, good. And then we need 0.98. And with 0.98, that means 0.98 is here. That means 0.01 is here. 0.01 is here. And so T naught, I look up 0.01, which was here. And so it's going to be 2.602. So 2.602. So T naught equals 2.602. All right. So that's a review of how to use the t-table. I hope that is a good review. So let's look at case 3. We have sigma unknown, n is less than 30. The data must be from a normal distribution or we can't use this method. And we could use the same, did we do a derivation? I guess we didn't. We could use the same derivation as we used before, but I won't do that. So the 100, 1 minus alpha % confidence interval is going to be x bar plus or minus, now it's T naught and S. That's what's different. And remember that T naught is going to be T sub alpha over 2 n minus 1 degrees of freedom. Okay, so we find alpha over 2 and n minus 1, we can find T naught very easily, and then we can plug in. And here are the 3 different ways we can write it. Okay. Now, with case 4, we don't have any requirements because we have the CLT. So everything's going to be the same, except n is now greater than 30, and we don't have this assumption. So this is what's different, the only thing that's different. Now, let's do example 4. We have a random sample of n measurements taken from a population that has a mean mu and a standard deviation sigma that is unknown. This is unknown. So we have the sample mean and the sample standard deviation given as x bar equals 507.5 and s equals 89.75. We want to find a 95% confidence interval for the population mean mu. This is C. So we'll go ahead and identify that. And A is going to be if n equals 20. Now this is less than 30, so we cannot use the central limit theorem. The data has to be normally distributed. Okay? It doesn't say that in the problem. And so this is one of the things I don't like about the book, but they ask you under C what assumptions are needed to justify the confidence limits in A and B. And of course, in A, it is that the data has to be normally distributed. I certainly wouldn't wait until after I did all the work to verify the assumptions. I'd do that ahead of time. All right? Okay. So as a general part of the solution, the only thing I can find when I don't have sigma, I can't find Z naught, which is common here to both parts A and B. I can't do that with T because T is dependent upon n minus 1 as the degrees of freedom. So for A, I'm going to have a different T value than I will for B. So what I can do is find alpha. Alpha is 1 minus C, which is 1 minus 0.95, which is 0.05. And we need, for confidence intervals, we always need alpha over 2. So this is 0.05 divided by 2 equals 0.025. Now, for part A, I need to find the degrees of freedom. Recall that the degrees of freedom is n minus 1. That's 20 minus 1, which is 19. So T naught is T sub alpha over 2 with n minus 1 degrees of freedom. We said that alpha over 2 is 0.025 and n minus 1 is 19. And so we need to look that up in our T table. And so I need 19 degrees of freedom, so I come down to where I can get to 19, and I'm going to underline that. And then I need 0.025. So here is the T sub 0.025 of R. So it's this column. So 2.093 is my value of T. So this is 2.093. Not a very good 3. Okay. Now, I've written this out separately. Again, as I said, I've written it out to be clear, different way of doing it, but I really prefer to do T naught S over square root of n like this because this term is common in both. So if I figure out that term, I'm in good shape. So the mean was 507.50. And then minus our T value, 2.093 times S, which was 89.75. My 9 doesn't look very much like a 9. I want to be careful with that. 0.75 divided by the square root of n, which is 20. And so this is going to be 507.50. I put this into my calculator and I get 42.00. And so 507.50 minus 42 is 465.50. That is my lower limit. And then I have 507.50 plus 42.00. And that is equal to 549.50. So this is my lower confidence limit, and this is my upper confidence limit. And I've already filled in our interpretation, we are 95%, that's C, confident that the interval, so I'm going to zoom in 465.50 to 549.50. That's a pretty big interval, isn't it? It goes from 465 to 549. Let's see what the difference, 549.5 minus 465.5. Yeah, 84, so 2 times 42. So the width of the confidence interval is 84. That's pretty big. That's a big interval. So n equals 20. Remember, we're dividing by the square root of 20. So n equals 20 is, that square root is between 4 and 5, so it's not very big. When we go to n equals 64, which is larger than 30, the square root of that is 8. It's going to be a bigger value. Was it 64 or 36 for B? 36. So we're going to be dividing by 6, so our interval will be smaller for that one. So we are 95% confident that the interval 465.5 to 549.5 contains the true population mean. We have nothing else told to us, so that's all we can say, using a random sample of n equals 20. Now, I need the degrees of freedom when n is equal to 36. That's going to be n minus 1 equals 35. So I need T of alpha over 2, 35. So 025. And I want 35. So the closest and lower value is 2.042, and so that's what I'm going to use. If you get above 40 here, just use the z value, okay, that's below it in the table. So for infinity, you've got, So for infinity, you'd have this, okay? You can see 1.645. This is 1.28, but 1.2, but it has one more decimal place than the z table does, okay? So this is going to be 2.042. S is 89.75. Yep. So X bar is 507.50 minus 2.042, 89.75 over the square root of 36. This is going to be 507.50 minus, so 2.042 times 89.75 divided by 6 is going to be 30.54. Let me check my t value. I've got 0.2535. 0.2535. 2.042 is the closest one and lower. Okay. So 89.75 divided by 6. Yep, so 30.54 equals, so 507.5 minus 30.54 is 476.96, and this will be 507.50 plus 30.54 equals 538.04. So the interval is going to be 476.96 to 538.04. We are 95% confident that the interval 476 to 5.96 to 538.04 contains the true population mean of whatever this is using a random sample of n equals 36. Part A, the assumption is that the data are normally distributed. And part B is none because of the CLT. Okay. All right, that does it for this section. I hope that this has helped you understand confidence intervals. If you have questions, come to virtual office hours. If you need help before then, by all means email me, but make sure that you email me a copy of or a picture of the problem so that I can have it available, because I may not. And then a picture of your work so far so I can see how you're approaching it and help you faster and better. Please take care of yourself, because